This is lecture 2.2 of Math 108, Indirect Proof. In this video, we will learn the two types of indirect proof, namely proof by contraposition and proof by contradiction. Consider a claim in the form of a conditional sentence, P implies Q. Recall that P implies Q is equivalent to its contrapositive, not Q implies not P. Hence, one way to prove the statement P implies Q is to give a direct proof of its contrapositive, not Q implies not P instead. This technique is called proof by contraposition. In such a proof, we begin with the assumption not Q and prove the conclusion not P. It will follow from contraposition that P implies Q. For example, consider the claim, if A is not equal to 0, then minus A is not equal to 0. Let P be the sentence A is not equal to 0, and Q be the sentence minus A is not equal to 0. Then the claim is a conditional sentence with antecedent P and consequent Q. We will prove this statement by contraposition. That is, we will give a direct proof of its contrapositive, not Q implies not P. We begin by assuming the negation of Q, which is the statement minus A is equal to 0. We will prove the negation of P, which is the statement A is equal to 0. It will follow from contraposition that if A is not equal to 0, then minus A is not equal to 0. Assume that minus A is equal to 0. Then, by the addition property of equality, the sum A plus minus A, which is the same as A minus A, is equal to the sum A plus 0. Since minus A is the additive inverse of A, it follows from the definition of additive inverse that A minus A is equal to 0. On the other hand, 0 is the additive identity element. So by the definition of additive identity, the sum A plus 0 is equal to A. Therefore, by the transitive property of equality, we have 0 equals A. Thus, by the symmetric property of equality, we get A equals 0. We have proved that if minus A equals 0, then A equals 0. Therefore, by contraposition, if A is non-zero, then minus A is non-zero. The second type of indirect proof is proof by contradiction, also known as reductio ad absurdum. This technique can be used for any claim with any propositional form. Recall that the conclusion not P follows logically from the premise P implies both Q and not Q. Replacing P with not P, we get the statement P follows from the premise not P implies both Q and not Q. Hence, one way to show P is to show that not P implies both Q and not Q. That is, we begin by assuming not P and deduce a contradiction Q and not Q. It will follow immediately that P must hold. Note that in this proof, we do not know what statement Q is, since this does not appear in the claim. It is up to us to determine whether or not such a contradiction has been proved. For example, consider the claim 1 is not equal to 0. The claim is a simple proposition P. The negation of P is the statement 1 equals 0. To prove P by contradiction, we begin by assuming its negation 1 equals 0. Our goal is to deduce a contradiction Q and not Q for some statement Q. Since a contradiction is a false statement, it follows that 1 cannot be 0. Assume that 1 equals 0. Let A be an arbitrary real number which is not equal to 0. Then, by the multiplication property of equality applied to the assumption 1 equals 0, we get that 1 times A equals 0 times A. Since 1 is the multiplicative identity element, 1 times A is equal to A. On the other hand, by example 3, 0 times A is equal to 0. So, by the transitivity of equality, we get that A is equal to 0. Thus, both A is not equal to 0 by the definition of A, and A is equal to 0 by our deduction above, which is a contradiction. It follows that 1 must be non-zero, as claimed. This ends the proof. This is the end of lecture 2.2. You may now proceed to lecture 2.3. Thank you for your attention.